And now we are going to see an example for this competency 1. Let's consider the liquid phase cis-strand isomerization of stibutane, which we will write symbolically as A goes to B. The first order minus Ra equal K Ca is carried out in a tubular reactor in which the volumetric flow rate B is constant, so B equal to B0. They ask us, derive an equation relating the reactant volume to the entering and exiting concentrations of A, the rate constant K, and the volumetric flow rate B. Second, determine the reactant volume necessary to reduce the exiting concentration to 10% of the entering concentration when the volumetric flow rate is 10 dm cubed divided by minutes. So that means 10 liters per minute. And the specific reaction rate K is equal to 0.23 minutes to the minus 1. And the third question is, sketch the concentration profile. So, solution. Number 1. Derive an equation relating the volume B, the volumetric flow rate B0, the entrance concentration Ca0, the rate constant K, and the exit concentration Ca. For a tubular reactor, the mole balance on species A was shown to be given by the equation dFA divided by dB is equal to Ra. And for a first-order reaction, the rate law is that the rate minus Ra is equal to K, the rate constant, times the concentration of A. Because the volumetric flow rate B is constant, B equal to B0, as it is in the liquid phase reactions, we will have that dFA divided by dB, and we can remember that Fa is Ca times the volumetric flow rate, so we will have d of Ca times the volumetric flow rate B, all that divided by dB, is equal to d of Ca times the volumetric flow rate at the entrance, which is B0, divided by dB. So, as the volumetric flow rate is constant, we can take it out, and we can say that this is equal to B0 times dCA divided by dB, and all this is equal to the rate Ra, according to the first equation at the top of this page. If we multiply both sides of this last equation by minus 1, and then we substitute the first equation at the top, we will have that minus B0 times dCA divided by dB is equal to minus Ra, which is the rate. But the rate is also equal to K times the concentration of A. If we rearrange this equation, we will have that dB is equal to minus the volumetric flow rate V0 divided by the rate constant K, all that multiplied by the dCA divided by Ca. And if we use the conditions at the entrance of the reactor when at a volume equals 0, the concentration of A is CH0, and at volume equal B, the concentration of A is equal to Ca, we will have that integral of dB is equal to minus V0 in K, which are both constant, the volumetric flow rate and the rate constant, times the integral of dCA divided by Ca. Carrying out the integration of this equation will give us that B, the volume, is equal to the volumetric flow rate divided by K, V0 divided by K, times the natural log of CH0 divided by Ca. And here again, we see that the volume of this reactor is given by the equation that B equal the volumetric flow rate divided by K times the natural log of CH0 divided by Ca. So the second question is, what volume B1 is the one that we require for a concentration at the exit equal 1/10 of the concentration in the entering the reactor. That means Ca equal 1/10 of CH0, knowing that K is equal 0.23 minus to the minus 1, and the volumetric flow rate V0 is equal to 10 liters per minute. If we substitute CH0, Ca, V0, and K in this equation for the volume, we will have that the volume is equal to 10 liters per minute divided by the rate constant, which is 0.23 minus to the minus 1, and multiplied by the natural log of CH0 divided by 0.1 CH0, which is Ca. So we will come to a volume of 100 liters or 0.1 cubic meters. Then we see that a reactor volume of 0.1 cubic meters is necessary to convert 90% of species A entering into product B for the parameters given. Third question. Species A is consumed as we move down the reactor, and as a result, both the molar flow rate of A and the concentration of A will decrease as we move through the reactor. By using the equation that the volume is equal to the volumetric flow rate divided by K times the natural log of CH0 divided by Ca, we can put different values for CH0 divided by Ca, such as CH0 divided by 0.9 CH0. Another value could be CH0 divided by 0.8 CH0, CH0 divided by 7.7 CH0, CH0 divided by 0.6 CH0, or CH0 divided by 0.1 CH0. And we plot all these values, we obtain the plot below.